I'm going to talk today about architecture. Do you know where the word architecture comes from? It comes from two words, archon, which is Greek for chief or leader, and texture, like technology. It comes from an Indo-European word that means to build. So it's chief builder. And it's actually a very romantic word and not one that we give enough credit to. And in many ways, it links the three topics that Auntie mentioned: technology, design, and craftsmanship. So I call my talk today Architecture, Language, and Design. And of course, when we think of architecture, we think of amazing structures, whether it is Brunelleschi's dome or whether it's an Amazon Web Services architecture for setting up Drupal. But in the end, those lines that we establish, someone thought, I'm going to do it differently. And then we think, oh, it's so obvious. But it's not obvious. And these people get lost. And I want to romanticize it a little bit. Let's talk about it a little bit. Think about why this is such an important and a task that we should celebrate. So with that, what is a good architecture? By the way, architectures are around us. Even the way a city is laid out today is based on an architecture. In fact, most Western cities are based on Roman architectures. Helsinki, when I arrived here yesterday, I noticed there were a lot of Chinese tourists at the airport. And I asked our friend Philip Mashke Pakala, I said, why are there so many Chinese visitors here? And he said that the Finns discovered this beautiful thing, that if you want to travel from China to Europe, Helsinki is on the way because of the Great Circle. And they leveraged it. So there is an architectural choice that Finland made. So what is a good architecture? We should think about it a little bit. So first of all, to me, the most important thing about a good architecture is that it offers you a simple design metaphor. Think about the World Wide Web. Before the World Wide Web, if you wanted to communicate, if you wanted to put some information, make it available, yes, you had the internet, but there was no clear metaphor. But now the metaphor is beautiful. I have a web page. That's it. I have a web page. And people can download my web page. And I have a hyperlink. And people can link on the hyperlink. Now, in retrospect, that seems so obvious. But I assure you, when I was a grad student, I didn't think of that. No one else thought of that. And the World Wide Web has transformed everything we do because it has a simple design metaphor. Okay? The same thing with digital electronics. I have a state, 1 bit. That's it. And that has transformed computing. I have flip-flops, I have gates, and I can design. So to me, that is the most important. But there are many more. The second is standardized interfaces. So with the World Wide Web, which I'll talk about more, you have standardized interfaces. There are only two, HTML and HTTPS. That's it. It's like Legos. You need to have standardized interfaces because if you have a nice design metaphor and you have standardized interfaces, then the human mind can become an architect for other systems. So this is what I call the sub-architecture, and then we build amazing things, and that's a super architecture. We can be both the archon and the texta, the builder. It's beautiful. By the way, the word textile also comes from architecture, as does my parent institution, the Massachusetts Institute of Technology, same root. So the third is you need to have abstraction and modularity. What that means is you need to be, of course, be able to live one level above the details. And you should be able to plug and play. And if you have standardized interfaces, that becomes possible. They're not the same thing. You can have standardized interfaces, but you may not have abstraction. You may have standardized interfaces, but you may not have modularity. So they're different things. The fourth is, and this is beautiful, and this is the 21st century. Not the 20th century, this is the 21st century. You've got to have scalability. Scalability both in performance and cost. What I mean by that is adding the next thing should be sublinear in cost and superlinear in performance. In other words, if you add another node, if you add another entity, then you need the cost to actually go down or the return to go up, and the performance has to be linear or maybe slightly worse than linear, but never a lot worse. So it's very beautiful. The next one is you have to have graceful failure. Very profound. Highly coupled architectures do not have graceful failure. Beautiful architectures have graceful failure. If a router goes down, the internet survives. If a web page goes down, or if there's a broken link, you get a 404, you move on. The system does not come down. Very, very beautiful. This comes with amorphous, lightly coupled systems have graceful failure. You must think about what happens when the you-know-what hits the fan. How will the system behave? The next one, very important, is you must enable repair and maintenance. Because after the honeymoon period is over, when you build something, when something goes wrong, can you fix it? If you have a highly coupled system which is very delicate, you cannot do that. Right? Our human body is very highly coupled. There are some things we can fix. And recently we figured out we've invented a heart-lung machine, and we can decouple. But we should be designing systems that are enabling of repair and maintenance. I'm going to explain an hourglass architecture in a minute. An hourglass is, that shape in which you put sand and you can measure time. That's the hourglass. I'm going to explain that in a little bit. That's a good principle. And then finally, especially in the age of Facebook, in the age of Google, your architecture must naturally be secure and must protect the consumer or the user's privacy. You cannot do this after the fact. And this is a mistake we make again and again and again. And then we act surprised. So with that in mind, let's look at, one other last thing. Great architectures are often counterintuitive. They're very obvious after the fact, but they're counterintuitive. In other words, the architect who said, let's do it this way or let's do it that way, is often shot or crucified, but in the end turns out to be right. That's the romance of it, okay? So around us everywhere are architectures. Even this is an architecture, the act of me standing on a stage and presenting, right? Maybe in 10 years, we will all be using virtual reality glasses, and I'll be sitting in my pajamas in Cambridge doing this presentation, and you don't have to see me in my pajamas, okay? Henry Ford invented the assembly line. This is Ford Gata, right? So he invented the assembly line, and this resulted in a transformation of the factory. Alternating current has an amazing story. I'm going to tell you that story. It is a heroic story, and it is an architectural decision that led to it, and it changed our economies. Packet switch networks, another heroic story. It changed the way in which we communicate. It was an architectural choice and a counterintuitive one, both of them. Cellular telephony, we all have cell phones and smartphones. Another counterintuitive architectural choice that has changed the face of humanity. The World Wide Web, another one, we just talked about it. Blockchain, I have mixed feelings about blockchain. Okay, people think it's a solution to everything, people think it's a scam. I'm in the middle, but I will tell you, I think it is a stunning and anonymous architectural design. To this day, it is anonymous. How stunning is that? Someday, someone will write stories about it, and we were all sort of in the middle of it. Cobotics, robotics and cobotics. I'll explain that. And so I'm going to introduce these technologies, but I'm also going to suggest to you, don't think of it as a technology. Think of it as a design language. So I want to come back to that. And then neural networks, invented 40, 50 years ago. Actually, much of neural networks came out of the artificial intelligence lab at MIT. Forgotten, dismissed, and came rushing back about 15 years ago because of data. And then finally, of course, IoT, which is the field I'm associated with. So I'll give you these examples. So let's go into some of them. Let's start with the power grid. So the modern power grid, all this electricity comes to us with, of course, as you know, alternating current, AC. But the story of AC is a surprisingly interesting and crazy one. These are all the people who contributed to alternating current. There are people who worked on the theory. There are people who worked on the motors and the devices. There are people who worked on the generators, people who worked on the transformers. But in this great group of people, there were two who were heroic. And they were Nikola Tesla and Westinghouse. And the story behind that is amazing. You may not know this. Edison, who, by the way, was a brilliant inventor and a Class A jerk, okay? Edison wanted DC, direct current. And he pushed very hard for it. He actually, if you can check it out on YouTube, actually I recommend you don't. He electrocuted an elephant to show that AC was dangerous. Actually, DC is more dangerous. But he wanted DC. Nikola Tesla pushed for AC, alternating current. And what AC does, and Westinghouse supported him. That's how Westinghouse, the company, grew. What AC does, as you know, although it is so counterintuitive, it is the natural form of electricity from rotating machinery. Because naturally, you get a sinusoidal wave. And with AC, you can do something amazing. You can step up with the transformer, step up the voltage, and then ship the electricity long distance. And because the current is so low, the I squared R loss is low. That's what made the modern electric grid, which is our supply chain, possible. And then you can step down at the other end, and then it naturally powers both rotating machinery, and it doesn't matter for bulbs. So we got light and we got motion. And it was all possible because of AC. And it was fought so hard by Edison. Tesla, who's a very elegant man, but he didn't make much money. He loved his clothes, he looked very smart, he was a brilliant inventor, he was a Serbian inventor. He lived in New York, he died in New York. But he never got, in his lifetime, the recognition he deserved, maybe a little bit. By the way, you should know that when Tesla died, a professor from MIT was invited to go and examine his properties in the hotel because they were worried it could be radioactive. You know what the professor's name was? Professor John Trump, uncle of President Trump. True. He was a professor at MIT. Anyway, the choice of AC over DC is a revolutionary choice in the history of technology. Here's cellular telephones. The cellular network, before the cellular network, connections were peer-to-peer. You had these radios, these walkie-talkie radios. So you talk to each other like this, direct, peer-to-peer. And cellular telephony is based on a very counterintuitive approach, which is even if I, in this room, call Auntie, in this room, I still go to the base station, and the base station calls the base station through my home, and it reaches him. Very counterintuitive, but actually fundamentally transformed telephony, cellular telephony, right? Now, by the way, the funny thing is, I was looking at this Ericsson 5G architecture a few weeks ago, and interestingly, what do you see again? For low latency, they're talking about device-to-device communication, something that was rejected in cellular telephony. People are talking about it again. It's interesting. We don't do it. We never do device-to-device. But 40 years later, we're talking about it again. Mesh networking tries to do that as well. So let's talk about the internet. Where did the internet come from? Well, before the internet, we had the plain old telephone systems, also called POTS, P-O-T-S. You made a phone call, But they used to have boys here, young men do this, but then they did not have the temperament to be patient. They would start screaming at people, so they kicked them out and they got women to do it because they're a little bit more polite. So this is a lot of women here. Anyway, when the phone call came in, they made a connection. And it was a fixed session, as you know, right? It was a session-based or a circuit-based approach. And then we automated that, and that's how the modern telephony system that I grew up in India came from. And then DARPA said, we want to create a different approach which protects our radar systems. Actually, much of this came from MIT, because they wanted their radar network in America to be protected from centralization and a single point of failure. They wanted graceful failure, easy maintenance, all the things I talked about. And so the crazy idea, as you know, was we will take data, break it into tiny packets, spray the packets into the network, and somehow they will make their way to the destination. It's a crazy idea and brilliant. Utterly brilliant. And at that time, they said, we'll never do voice. Well, we do voice. We'll never do video. We do video now. And the reason is, once that idea was born, every router had a standardized interface. And you had a design metaphor, a router, and an IP address. And boom, here we are in 2018, using WhatsApp that goes over this, using Facebook that goes over this, shopping at Alibaba or Amazon that goes over this. And there are people, of course, there are a lot of stories written about these people. They were considered fools in their time, but we celebrate them today. And by the way, it captures all the principles I talked about from an architecture perspective. It's a simple design metaphor, standardized interfaces, abstraction, modularity, scalable, graceful failure, easy to repair. I'm going to talk about Hourglass. Remember I said Hourglass architecture? I'm going to talk about it next. We did not make it that secure and private. That is the one thing we have to worry about today. And you cannot do it after the fact. But it was counterintuitive. Okay. What's an hourglass architecture? This is what an hourglass architecture is. If you look at the internet, you have the stack is a big one. You have the applications on top. You have protocols like HTTP, SMTP, etc., etc. You have TCP, IP, UDP. Sorry, TCP and UDP. Below you have copper. You have all these different ways of communicating with optics, fiber optics. You have Sonnet. Actually, Helsinki did a lot of work on Sonnet. Sonera was the great pioneer there. Ethernet, etc. But the one thing we all agreed on was IP. So the lesson there is, it's okay if you have a lot of chaos, but you need to pinch in one place and say, there we agree. The same with telephones. We agree on the country code. That's it. Once you have the country code, every country can do what it wants. It's the same with IP. We agree on IP. Everything else doesn't matter. But once you agree and you standardize, you have a design metaphor, and you can generalize. And you have all the other benefits. The World Wide Web is another wonderful example. This is, of course, Tim Berners-Lee. He's a colleague of mine at MIT. He was a young man at CERN in Geneva. And he wanted to figure out, this is in the late 80s, how researchers could share documents with each other. And what a stunning, beautiful thing he came up with. Stunning. He said, and before that, I used to hack FTP and Telnet. I was an expert in Telnet in the late 80s. But he said, no. You don't need all that stuff. In many ways, and this is the beauty of architecture, he said, you need less than what you have. Many architectural choices are not about expanding, they're about reducing. This is the great thing about Steve Jobs as well. Steve Jobs reduced your architectural choices. It's a beautiful concept. And he said, you need hyperlinks and you need HTTP. That's it. Look at that. That's it. Pages and hyperlinks. Done. And this is the World Wide Web as we know it today. And that little piece of elegance, that little piece of frugality, unleashed on us the most important thing today, which is Google, which is the search, biggest app, but I'm joking. Millions of applications that sit on top of it, right? I actually went and did some research. I found the original World Wide Web Consortium is headquartered at MIT. I did some research for this, and I found the original document. And, you know, I can imagine him going to his, boss's office and saying, I have this crazy idea. And his boss looks at it and says, what is this? Well, his boss didn't do that. His boss was somewhat open-minded. He wasn't an IT expert, he's a physicist. And this is what led to the World Wide Web. That's worth a read, by the way. If you go to the World Wide Web and go to the history section, read it, because it's very inspiring. It gave me goosebumps. And of course, the growth has been stunning. You know, I was talking to a fisherman in India the other day, and when the fishermen come back from the port, these are poor people in boats, in very tiny boats, canoes. He says, I pull out my phone and I see which port I should go to see what the spot prices are for fish. That is the extent to which this has impacted the world. Blockchain is another amazing story. Romantic, amazing, perhaps completely useless, perhaps world-changing, we don't know. Okay? But it is a beautiful story. And the beauty of it to me is the architecture. We traditionally love centralized things. If you look at the history of the world, it has been a pendulum swing between distributed and centralized. Distributed governance, like in Athens and Sparta and Corinthos in ancient Greece, to centralized, the Roman Empire. Before the Roman Empire period, the Rome was distributed, it was a democracy, and then became centralized with Julius Caesar. The same in India, the same in China. Egypt was always centralized, right? In Europe, you know, even in the last 100 years, you've seen the sweep of individuality and centralization. Centralized systems are easy to control. Most of our IT systems are controlled and centralized. And so the fact that this guy comes along, and we don't know who this person is, and he takes these centralized systems and he says, let's decentralize them a little bit, and oh, by the way, let us completely decentralize. There is no owner, there is no leader. It's all by vote. It is all by what is called consensus, right? Consensus has been studied for 40 years. In fact, Leslie Lamport, who's an MIT guy, and Barbara Liskov, they wrote the Byzantine algorithms they've worked on the Byzantine algorithms for consensus computation in distributed systems. We've known that for 40 years. But to take that, to set up a voting mechanism, to invent this extraordinary scheme, where anyone who wants to transact, all they have to do is basically throw the transaction into the soup, as it were, and the transaction is blocked up, and then there's some crypto magic, and then gets thrown into the ether. And you have all these systems around the world racing to digest it. And within minutes, tens of minutes, it's done, and you have distributed consensus. It's pretty stunning. Now, I have concerns about it. I mean, the concerns have to do with any voting mechanism can be gamed. If a single country controls too many of these servers, that could be a problem. We'll figure it all out. But the concept is amazing. And we still don't know who Satoshi is, and we still have rumors about who Satoshi is. Catch me later on, I have a conspiracy theory. If you're interested, I'll tell you. But this, to me, is the epitome of the craft of architecture, the hidden hero, sometimes forgotten, or heroine, sometimes forgotten. But the beauty is everlasting. Robots. When we think of robots, we think of R2-D2. We think of an arm, right? But actually, robots have evolved in very different ways, and it comes down to architecture. For example, who the hell thought that the Roomba, which is Rodney Brooks, one of my colleagues, would be the most distributed robot in the world for doing what? Vacuum cleaning. Right? That's an architectural choice. He didn't think of fixed robots. He didn't think of robots that go around serving your coffee. He focused on a very particular application. And now the same Rodney Brooks has a new company called Rethink Robotics, and the whole field is moving towards not robotics, but cobotics, where the robot is your assistant. And what the cobot does is you can literally hold it and train it, and it works with you. The fixed hard robots are dangerous. People have died. There are many documented stories about people dying. But what I'm going to show you next is, for me, a beautiful story of robotics. And it's based entirely not on the robot, but redesigning a warehouse and the architecture to enable better performance. So, volume up. Can we increase the volume? I'm going to replay it. Okay. Sorry. Shall I play it? Is the volume up? Okay, just give it a second. Actually, I'm not concerned about the volume because I can tell you what he's saying. So this man is a friend of mine. He and his frat mates at MIT decided they were involved in a company called Webvan. Do any of you remember Webvan? Webvan, yeah, is one of the largest venture capital failures in history. And what he's explaining is why Webvan failed. And it turns out the reason Webvan failed is because taking pallet loads of things is like a home delivery system. It was set up about 20 years ago. And the reason it failed is warehouses were not designed for bringing in truckloads of stuff and taking out one of something. They were designed for bringing in truckloads and taking out a pallet.
For how it should work.
Okay, so let's play this again. Okay.
Material handling was set up to pump pallets and cases of goo to retail stores. Of course, Webvan went out of business, and about a year and a half later, I was still noodling on this problem. It was still nagging at me, and I started thinking about it again, and I said, let me just focus briefly on what I wanted as a pick worker, or my vision for how it should work. I said, let's focus on the problem. I have an order here, and what I want to do is I want to put red, green, and blue in this box right here. What I need is a system where I put out my hand and poof, the product shows up.
I put out my hand and poof, the product shows up. So how would you design a system like that? Today, the way it works is you walk around the warehouse with a trolley, you pick up something, put it in. He said, let me rethink the architecture of the warehouse. Instead of the delivery worker going to the shelf, I will have the shelf come to the delivery worker. And that, ladies and gentlemen, is a company called Kiva Robotics. It was acquired by Amazon for about $750 million
Material handling
4 years ago.
Set up to pump. It speaks to the power of emergence in systems when you let things start to talk with each other. So that was a little bit of the journey. So of course, now what became the practical reality of this idea? Here is a warehouse. It's a pick, pack, and ship center that has about 10,000 different SKUs. We'll call them red pens, green pens, yellow Post-it notes. We send the little orange robots out to pick up the blue shelving pods, and we deliver them to the side of the building, so all the pick workers now get to stay on the perimeter. And the game here is to pick up the shelves, take them down the highway, and deliver them straight to the pick worker. This pick worker's life is completely different. Rather than wandering around the warehouse, she gets to stay still in a pick station like this, and every product in the building can now come to her. So the process is very productive.
Ladies and gentlemen, that's an architectural choice. It's not a new technology. It's a warehouse architecture. I'm going to go quickly now and just say a few more things. Right now, the Internet of Things, my field, does not have an architecture. It is frozen by the lack of an architecture. We shouldn't call it the Internet of Things. We should call it the cobweb of things. Today, if you want the lights in this room to be controlled to the door, some vendor might come along and use Wi-Fi. And if you want the air conditioner to be controlled by another door, another vendor is going to come by and use, I don't know, Zigbee. And then you want the lights and the air conditioner to be connected. A third vendor will come along and use 6-low-pan. And at some point, something's going to break. And then chaos will ensue. It's not modular. It's not maintainable. It's not repairable. There is no graceful failure. There is no abstraction. It is a mess. And so one of the things we're proposing in the Internet of Things is that we need to design a new architecture. And the basic idea that we are proposing in my group and others, in fact, the term, so we came up with the term in about 2010. The term was cloud things, not Internet of Things, cloud things. And at the same time, NASA came up with the term digital twin. So that, I think, is the future. So the basic idea is everything in the real world has an avatar in the cloud. And that is a simple architecture. And when two things want to talk to each other, as much as possible, they talk through the cloud. And so we're pushing this, and I have a feeling that this may actually address some of the issues that we're facing with the Internet of Things. The lack of an architecture is the problem. And once we figure that out, then we'll have an opportunity to make IoT as common and as successful as some of the other things we've done. And we call it cloud things and digital twins. And so if you think about it in an hourglass way, what we're saying is it doesn't matter how you communicate here, whether it's Zigbee or whether you use bridges or they use other stuff. The point is take everything to the cloud and then communicate across the cloud. So the cloud is where things get pinched together. If you need real time, do it real time. If I press the brake on my car, I do not want it to go to the cloud before it tells the ABS, okay? I want it to be real time. So I get it. But in most applications, like the door and the light, you don't need sub-millisecond response. And you can use the cloud. And one way, if the cloud is too long, is you bring the cloud close. You create a proxy for the cloud close to the ground. And what do we call a cloud that is touching the ground? Fog. And so that is edge computing or fog computing. So this is what we propose. Anyway, I'll skip that. I'll skip that just in the interest of time and just say two other things and then I'll end. Computing is going through a revolution. So our modern computing system is based on a Hungarian immigrant to America, von Neumann. Most of you probably may or may not even know his name. He was a great mathematician, physicist. He knew Einstein. But people don't realize he actually created the modern computing architecture, which is based on a control bus, a data bus, an address bus, CPU, memory, input, output, etc. What's happening today? What's happening today is the neural network. And the neural network is based on the human mind. It's actually very modular, and it's very self-healing. The problem with the neural network was we could not handle the training. And today, what's happening is this new architecture, because of the World Wide Web and Google and Facebook, and because of our capabilities with data, we can suddenly handle the training. That's all that's changed. And suddenly now, this may be the modern new architecture for computing. Now, of course, today we implement neural networks on traditional computers. And IBM and MIT signed a $250 million deal last year to say that we will start designing the hardware of the future and new architecture. Okay? I'm not going to talk about quantum computing. There's a whole other effort in quantum computing. I think it's early days. I think we're about 5 years away. What quantum computing is another place where all this will happen. So now let me sort of summarize and say that, so what do architectures do? So the way to think of architectures is Um, here's the way I think about all technologies. All technologies give us a new language. So I was talking again to Philip yesterday. Hungarian and Finnish, as you know, and Estonian and Mansi and the Ugro-Finnic languages are all related to each other. But they're separated by 4,500 years. So some of the words are the same, but only about 200 words. The one thing that never changed is the architecture of the languages. The architecture of a language is the grammar. So let me use the analogy of language and take it a step further. In my view, ladies and gentlemen, technologies give us new nouns and new verbs. For example, when a teenager says to another teenager, I will WhatsApp my location to you. I will WhatsApp my location to you. She's assuming WhatsApp, wireless networking, GPS, Google Maps, etc., cell phones, social networking, etc. So I will WhatsApp my location to you it's a new verb and a new noun that has so much technology in it. But underlying all that is a grammar, which is cloud, cellular network, the cellular architecture, the internet, the World Wide Web is all underlying that. So to me, new technologies give us new verbs and new nouns, and the grammar is the architecture. Okay? So essentially, when you come across a new technology, when something new happens, think of it as a powerful new language at your fingertips, with the grammar as the architecture and the nouns and verbs as the capabilities. So if you look at IoT, IoT is actually several new words. We can connect things, connectivity, right? I can remotely operate something. But it's actually many more things. I'm just using IoT as an example here. It's computation. So your Nest thermostat working with the cloud, or your Alexa working with the cloud, can figure out your needs. Sanjay, you don't come home until 7 p.m. Why are you turning the heating on at 5 p.m.? You'll save 10% of energy if you change the heating schedule. That's computation, right? The third new noun or verb in IoT is recruitment. So for example, my Mac I can log into it with a password, I can log into it with my fingerprint, but I have an Apple Watch. I can log into it with my Apple Watch. In future, my coffee machine, when I go up to it, instead of asking me to press the button, might simply detect the Bluetooth on my Apple Watch and say, would you like me to make you a ristretto? In fact, it might say, Sanjay, your blood pressure is a little high today. Maybe you should have decaf. Okay? So those are the new nouns and verbs, and that is what I call recruitment, where devices are recruiting each other. And the final is immersion. Immersion is a world in which we're immersed in information. So when I'm listening to music on the way home, when I park my car and I step into my living room, the music follows me. When the telephone rings, my AirPods pick up the telephone, pauses the music from my high-end system, and then returns to it when my phone call is ended. Right? When I wake up, my Apple Watch tells my clock, listen, he's getting some really good rapid eye movement sleep, REM sleep. And he doesn't have an appointment for the next 90 minutes. Let him sleep another 10 minutes. And maybe it hits the seats in my car in a Boston winter. Right? That's immersion. So to me, these are the new nouns and verbs that IoT creates. Machine learning gives us new nouns and verbs. But the underlying architecture is the grammar. If we have all that, then we can invent new experiences. And what is happening again and again is large companies are not realizing the stunning capabilities that these new narratives that we can construct give. And they're falling prey again and again to disruption. And the disruption is coming from companies like Uber and Airbnb and Zipcar. And if you're wondering what this is a company called 8 Sleep. I'll end with this. 8 Sleep decided people don't want to buy mattresses. People want sleep. And what they've invented is a smart mattress that makes sure you sleep well and heats and cools, measures how well you slept, changes the stiffness, etc., etc. And this is all possible because of this new grammar and the new technologies which create new verbs and new verbs and nouns, and the new narratives we can construct to meet the user's needs. I actually have a book on this topic. Basically what we're saying is if technology changes, the business architecture must change, and companies are not doing that. And that's the book. But anyway, thank you very much, and a great pleasure to be here in Helsinki.